trapping ions in order to do more fundamental physics research eventually. So right now we're trapping barium ions as a tool to be able to cool molecules. We trap it in what's called a Hall trap. So we have basically 4 rods like so, and the other 2 are behind these, and then we have plates over here. And looking down this way, 4 rods are like this. And what we do is, in order to trap these ions, we put a radio frequency voltage, basically just time oscillating voltage, on those 2 rods, and we ground these. So what an ion sees in the center here is, inside, if these are positively charged, it's repelled away from these 2 rods, so it might move a little bit towards a ground rod. And then the next instant of time, these are negative, so the ion's attracted back. So that keeps it confined in that area there. These 2 end plates here, we just put a voltage on, and it keeps the ions centered in here. And hopefully later, we can make or have enough ions that you can see them with your naked eye versus a camera, which should be really cool. So, see in there now, you see the 4 different rods? Yeah. And then the metal end caps. So that's the entirety of our trap. And currently, we have barium ions in it. That camera is live of the different barium atoms fluorescing inside the trap. So because you can see the individual ions, they're very cold. It's actually formed a crystal in there. So they have the trap pulling them all together towards the middle, and then since each ion repels itself, they kind of each fall into a local area where they're happy energetically. To do the cooling of this, of barium in the trap, we use lasers, which is kind of counterintuitive because you think lasers, a lot of light, it would heat up barium. But we play a neat little trick. So an atom has an absorption curve kind of like this. So if there's a certain width here, it's almost like a bell curve, and a central color. This is the wavelength of the transition, and then we have this width. So what we do is we tune our laser not here, but a little towards the lower energy side. So every time the atom is moving around, it needs that little bit of extra energy to absorb. So each time the atom absorbs a photon, and then re-emits it in a random direction, it loses a little bit of energy. And that's how we cool the barium. And they actually get cold enough that you can see individual ions in the trap. The level structure of barium, it's like this. And these are the cooling transitions here. So this one is 493 nanometers, and this one here is 650 nanometers. So in order to cool, we drive primarily this transition, so it cycles back and forth along here many times before every once in a while it'll fall into over here, so we repump it back to this state with the 650 nanometer laser. And the reason we use barium is because these 2 wavelengths are both the most red. Where all those others, this transition here is in the ultraviolet. And there's some subtleties with that involving molecules, because a lot of the molecule transitions are in the UV. And we don't want to mess with the molecules. We use the 650 nanometer laser and the 493 nanometer laser. Both systems are on the other table, and then we bring the light here by optical fiber. So here, for example, is the red light, which is the 650 nanometer, and here is the blue light, which is that 493 nanometer. That camera is live of the different barium atoms fluorescing inside the trap. So because you can see the individual ions, they're very cold, it's actually formed a crystal in there. So they have the trap pulling them all together towards the middle, and then since each ion repels itself, they kind of each fall into a local area where they're happy energetically. That's what allows that. If they're hot, they'll get very blurry, you can't individually see them. Or if I move it back to where it used to be, you should see, it should get nice and happy again. It's fast, it's very controllable, we can get to very low temperatures with the laser cooling. So in the ion crystals, when you could see the individual ions, those ions are probably in the millikelvin temperature range. So less than a degree from absolute zero. And that's only achievable with the laser cooling of the ions in that trap.
So, once you cool these ions, you talked about how they would be able to cool molecules.
Mm-hmm.
Okay, and so what would you then do with cooled molecules? Like, what are you guys trying to research? Like,
so first we want to do spectroscopy on those molecules, and we have some interesting ideas of how to get the molecule to what's called the rho vibrational ground state. So using barium, we can make them translationally cold. But then there's still, the molecule can vibrate, it can rotate. And we have some interesting ways to get them so they're not vibrating and they're not rotating anymore. And then do our spectroscopy. So that's first what we're going to be doing with our chamber with aluminum hydride. And then later on, we want to probe in our lab things like variation or time variation of fundamental constants. So for one example, there's a ratio of the proton mass to electron mass. Well, for all intents and purposes, up until the 13th or 14th digit of that number, it's constant. But then the last digit may vary with time. And that's something that we can measure and hopefully probe with experiments in our lab, because no one has been able to measure that accurately.
how did you get involved with the lab? Describe your relationship with Dr. Odom. I know he's like in charge of that.
So first I'll mention of how I ended up working in that lab. I knew I wanted to go to graduate school. When I graduated college, I knew that I wanted to do something experimental, definitely, either in atomic, molecular, and optical physics, which is what we're doing in the lab there, or in condensed matter.
What about practical applications of this? Where are you going for practical uses?
Practical uses, it's a fantastic question. So there's both the fundamental physics side and the experimental side. For the fundamental side, if we know and have better models of physics, we get better technology down the line further. Two examples that I love bringing up are, one, the transistor. That was theorized it could work by physicists with the data they had at the time, the theories they had at the time, and then they built it, and now look at our world. Another great example is lasers. So, even some cars now are thinking of using lasers in order to generate their light for their headlights. In fact, I think that is Audi who's doing that. But that is what once was just a theory and a lab experiment has turned into something that people will have in their everyday life.